Hi everyone. So let's continue with lecture 9 and let's start with an example to produce the graph of the function f of x equals x plus 2 over x minus 1. So first, as always, domain x belongs to the real numbers except from the root of the denominator, which is positive 1. Second, find the intersect points with the axis. So for x equals 0, we have f of 0 equals 0 plus 2 divided by 0 minus 1. We have 2 over negative 1. And so f of 0 is negative 2. And so the intersection point is 0, negative 2. Now for y equals 0, it means f of x is equal to 0. So we have x plus 2 over x minus 1 equals 0. Whenever we have a fraction to be equal to 0, only the numerator can be equal to 0. So x plus 2 is equal to 0, x is negative 2, and so the intersection point is negative 2, 0. So step 3 is the monotonicity. So I copied the formula of the function so that we can remember it. And we go f prime of x. This is x plus 2 derivative times x minus 1 minus x plus 2 times x minus 1 derivative divided by the denominator x minus 1 quantity squared equals derivative of x plus 2 is 1 times x minus 1 minus x plus 2 times the derivative of x minus 1 again times 1 divided by x minus 1 quantity squared equals, we can do the operations now, x minus 1 minus x minus 2 over x minus 1 quantity squared. The x's cancel and we get negative 2 divided by x minus 1 quantity squared. And this is equal to 0. So no roots of numerator, so no extreme points. However, we do have the roots of the denominator, which is x minus 1 cannot be equal to 0, and so x1, 2 cannot be equal to 0, and this is a double root. So we continue by constructing the sign table in order to place the double root of the denominator, like so. This is one double root, but because we don't want it to be 0, we place the parallel lines because this is a singularity. On the right hand side, we can see that there is a concentrated negative sign on the entire fraction. X minus 1 quantity squared is always positive, and so with the negative sign, our derivative becomes negative to the far right, and because it's a double root, the negative sign remains to the left side. And so the function is decreasing and decreasing. So we can say that f of x is decreasing for every x value except x equals 0. We continue with the concavity. And here we can see that if we bring this bracket on the denominator to the top, the function becomes f prime of x equals negative 2 times x minus 1 to the negative 2. We do that because we can exploit the formula f to the n of x derivative equals n times f to the n minus 1 of x times f derivative of x. So there is no need to use the quotient rule. So we use the power rule instead, and thus making our lives easier. So f double prime of x is going to be negative 2 brackets minus 2 times x minus 1 to the negative 3. We reduce the exponent by 1 times x minus 1 derivative. And we know that the derivative of x minus 1 is 1. And so let's tidy this up. We have negative 2 times negative 2. We have positive 4 times x minus 1 to the negative 3. So let's bring the brackets back to the denominator. So this is equal to 4 divided x minus 1 quantity cubed equals to 0. So once again we can see we have no roots on the numerator. So no inflection points. But we do have roots of the denominator, just like before. X minus 1 quantity cubed cannot be equal to 0, and so x1, 2, 3 cannot be equal to 0, and this is a triple root that we are going to use later. Continuing on, we make another sign table for the concavity, and we place 0 as our triple root, once again as a singularity with the parallel lines. And now the concentrated sign of the fraction is positive, but the root is triple. So this is going to be positive, and on the other side is going to be negative. And so concavity will be like so. So concave down for the left side and concave up for the right side. Remember that this is a singularity, and it doesn't matter that the sign changes both sides. This is a singularity, so no inflection points. Don't get confused. So we continue with the limits at the edges of the domain. We take limit x goes to positive infinity of x plus 2 over x minus 1. You know very well that if we substitute, this is going to be infinity over infinity, which is undefined. Obviously, we learn the technique to take only the highest order term when we have polynomials, both at the top and at the bottom, so we can use that as well. Limit x goes to positive infinity of x divided by x. They are simplified, 1 over 1 equals limit x goes to positive infinity of 1, which is equal to 1. Or we can use DLH, which is the limit x goes to positive infinity of x plus 2 derivative over x minus 1 derivative, which is limit x goes to infinity of 1 over 1, which is also equals to 1. So both techniques are accepted. You can use whichever technique you want. In this case, because we have a rational polynomial function, we can use both techniques, but if we have other functions like logarithmic, exponential, and others, we must use de L'Hopital. So we have found that for positive infinity, the function doesn't get infinite itself. It gets close to 1. The same thing if we do for negative infinity. I leave that to you. And so, since the limit of the function at infinity, either to 1 or both sides, gives us a real number, it means that the function has a horizontal asymptote. So a limit towards infinity, plus or minus infinity, giving a finite or real number, is what we call a horizontal asymptote. And so y equals 1 is a horizontal asymptote. And this is very important. Remember that we had a restriction that x cannot be equal to 1, so we must take the limit and see the behavior of the function near the restricted value. So we take the lateral limits, limit x goes to to 1 minus of x plus 2 over x minus 1 equals 1 plus 2 divided by 1 minus 1. So it will become 3 divided by 0 minus, because this number is a little bit smaller than actual 1. So the 0 is going to be on the negative side. So this results to negative infinity. If we do the same thing for the other lateral, limit x goes to 1 plus of x plus 2 over x minus 1 equals 1 plus 2 over 1 plus minus 1 equals 3 divided by 0 plus. So this is going to be equal to positive infinity, not negative infinity, positive infinity in this case. And we can see that a limit towards a finite number giving plus or minus infinity, or both in this case, is what we call a vertical asymptote. So whenever we have restrictions, we must take this limit as well. And so x equals 1 is vertical asymptote. So since we have everything ready, we can plot the graph. Let's do the preparations first. So we prepared the Cartesian system, the vertical asymptote and the horizontal asymptote. Let's place also the intersection points, which is at negative 2, 0 and at 0, negative 2. So there is no extreme points nor inflection points, but we know that the concavity to the right side of positive 1 is going to be upwards, and the concavity on the left side is going to be downwards. So the graph is going to be like this. So asymptotically, positive infinity at 1 plus, negative infinity at 1 minus, and from the looks of things, we are going to have the 1 plus on the horizontal asymptote and 1 minus on the other side at negative infinity. So the right branch will be something like this, and the left branch will be something like this. And that is the graph of this function. So now you can see the graph being produced by the program Desmos, and you can compare this with the notes. So here is the horizontal asymptote at x equals 1. As you can see, the graph on both sides approaches that value 1, but it doesn't get it exactly. And here is the vertical asymptote at x equals 1, that you can see they are the y values that blow up to both negative infinity and positive infinity respectively, and also the 2 points, the intersection points with the x and y axis respectively. Let us continue with another example. So we have y equals x squared minus x plus 1 divided by x, where this is a special case in which the order or the degree of numerator is 2, while the order of the denominator is 1. So this is not the special case because the order of the numerator is 2 and the order of the denominator is 1. Rather, the difference of the order of the numerator minus the order of the denominator is 1. So only when the order of the numerator is by 1 greater than the order of the denominator, the plot does not have a horizontal asymptote, it has an oblique asymptote instead. So we have an oblique asymptote, a lateral asymptote, that we are going to see how to calculate. Let's do the procedure once again. Step number 1, we have the restriction, x cannot be equal to 0, and so the domain, x belongs to the real numbers except 0. Step number 2, we cannot take x equals 0, so the only intersection point we have is going to be on the x-axis. So for y equals 0, f of x equals 0, and so x squared minus x plus 1 over x is equal to 0. So only the numerator can be equal to 0, x squared minus x plus 1 equals 0. But this polynomial is not factorizable. Let's check its discriminant. D equals b squared minus 4a times c. This is going to be equal to -1 quantity squared minus 4 times 1 times 1 equals 1 minus 4 equals -3, which is negative. So this polynomial has no real roots, and so we don't have any x nor y intersection points. So no x, y intersect points. Step number 3, y prime equals x squared minus x plus 1 derivative times x minus x squared minus x plus 1 times x derivative divided by x squared. This is equal, we have 2x minus 1 times x minus x squared minus x plus 1 times 1 divided by x squared. We can expand the brackets because we cannot factorize from this stage. So 2x squared minus x squared plus x minus 1 over x squared. So we can see that x cancels and we are left with 2x squared minus x will give us x squared minus 1 over x squared, which is a difference of squares, so we can say x minus 1 times x plus 1 over x squared, and this is equal to 0. So we have two real roots and a double root, x equals to 0 of the denominator. So x1, 2 is plus or minus 1, while x3, 4 cannot be equal to 0. And let's go ahead to construct the sign table. So let's place the roots of both the top and bottom. We have -1, we have 0, that is double, and we have +1. These two are the zeros of the function, whereas this is the singularity of the function with parallel lines, and this is the final factorized form before we solve it, and we can see that there is no sign outside of the fraction. X squared is positive and both x's in the brackets are positive. So the rightmost interval will be positive, negative on the left of +1, negative because it's a double root on this section, and on this section is going to be positive with increasing and decreasing, decreasing and increasing. So we can clearly see we have a maximum on this side and a minimum on this side. Let's go ahead and calculate them. So f of -1 is going to be -1 quantity squared minus -1 plus 1 divided by -1. This is equal to 1 plus 1 plus 1 over -1, so this will give us -3. So the maximum will be -1, -3. Now for the minimum, f of 1 equals 1 squared minus 1 plus 1 divided by +1. These two cancel, and we have 1 over 1, which is 1, and so the minimum is 1, 1. You might say, but how is this possible that the minimum value is greater than the maximum value? The reason is the function is discontinuous at x equals 0. Had the function been continuous at x equals 0, then possibly the maximum value would have been greater than the minimum value locally. So let's write the monotonicity intervals. Increasing, x belongs from -infinity to -1 closed, union from +1 to +infinity open. Decreasing, this is x belonging from -1 to 0 open, union, open interval 0 to +1, and we can do this so that we skip x equals 0. We're not going to take the interval from -1 to +1 as a single unit. Step number 4. Let's remember first y prime equals x squared minus 1 over x squared. We are not going to use the factorized form because we would have, apart from the quotient, we will have a product to deal with, whereas in this form, the derivative is calculated much easily. So the second derivative, y double prime, is going to be x squared minus 1 derivative times x squared minus x squared minus 1 times x squared derivative over x to the fourth equals 2x times x squared minus x squared minus 1 in brackets, don't forget them, times 2x divided by x to the fourth. We can clearly see from this stage that we have this and this to be common factors. So let's do the factorization from this stage so that the equation we would solve at the end is already factorized and it's not very complicated. So this is equal to 2x square brackets x squared, and let's get rid of the brackets here, minus x squared plus 1 divided by x to the fourth, and here we can simplify. Also the x squares in the brackets cancel, so we are left with 2 times 1, which is 2, divided by x cubed equals to 0. So no roots of the numerator, so no inflection points, and also x 1, 2, 3 cannot be equal to 0, triple. So let's place 0 as a triple root and as a singularity. On the right hand side we will have a positive sign and a negative sign of the triple root. Also let's say f double prime and f of x, concave down in this interval and concave up in this interval. Once again, this is not an inflection point because this is a singularity. It is a value that we cannot take. And the concavity intervals, concave up, x belongs open from 0 to infinity open, and concave down, where x belongs from negative infinity to 0 open. Step number 5. Let's check the limits at infinity. Limit x goes to either positive or negative infinity. You will see why. X squared minus x plus 1 over x. This is a polynomial rational function, so we just take only the highest order terms of the numerator and denominator equals limit x goes positive and negative infinity of x squared over x. We simplify the square with x, so this is equal limit x goes to plus or minus infinity x, and this is going to be respectively plus or minus infinity. So obviously, since the limit to infinity gives us infinity, there will be no horizontal asymptote. So let's continue with the restrictions. We have one restriction at 0, limit as x goes to 0 minus x squared minus x plus 1 over x. We substitute 0 minus 0 plus 1 divided by 0 minus. We have 1 over 0 minus. This will be negative infinity. And limit as x approaches 0 plus x squared minus x plus 1 divided by x equals 0 minus 0 plus 1 over 0 plus equals 1 over 0 plus equals positive infinity. So the singularity will give us a vertical asymptote x equals 0. Because it's vertical, it's going to be x equals something. X equals 0 in this case. But as we said in the beginning, since the order of the numerator is by 1 greater of the order of the denominator, it means we have to check if we have an oblique asymptote. So the rule is, if we don't have a horizontal asymptote, we need to check if we have an oblique asymptote. And also the model of the oblique is the straight line model, y equals mx plus c. So we are going to use this during our calculations. So we start with the gradient of the oblique. M is equal to the limit as x approaches plus or minus infinity f of x over x. So we do this first, and if this is a real number, then we continue for c. So let's find this first. Equals limit x goes to plus or minus infinity of x squared minus x plus 1 over x divided by x over 1. So because of this situation, we are going to have a composite fraction. So instead of doing this, let's do this. So the limit as x goes to plus or minus infinity of 1 over x times f of x, which is x squared minus x plus 1 over x. And obviously this is within brackets. We can multiply the numerator with the numerator and the denominator with the denominator. Equals limit x goes to plus or minus infinity of x squared minus x plus 1 divided by x squared now. And we take only the highest order terms. Equals limit x goes to plus or minus infinity x squared over x squared. They both simplify each other, and so the gradient of our oblique will be equal to 1. So since this is a real number, we are going to continue with the next formula. C equals limit x goes again to plus or minus infinity of f of x minus m times x. So let's substitute. Equals limit x goes to plus or minus infinity of x squared minus x plus 1 over x minus 1 times x, which is the gradient. In this case, we have a difference of fractions, so let's make them like first. Times x times 1 equals limit x goes to plus or minus infinity x squared minus x plus 1 minus x squared divided by x. The x squares cancel, and we are left with equals limit x goes to plus or minus infinity of negative x plus 1 divided by x. Once again, we are leaving only the highest order terms, equals limit x goes to positive or negative infinity minus x over x. They cancel, and so c is going to be negative 1. Thus, the oblique asymptote now is y equals x minus 1. And now we are ready to plot it. So I have done the preparation. Here is the Cartesian system, and this is the oblique asymptote, which is once again y equals x minus 1. So when x is equal to 0, it passes from negative 1, and when y is equal to 0, x is equal to positive 1. The vertical asymptote is the y-axis itself. When we have the limit at 0 plus, we get positive infinity, and at 0 minus, we have negative infinity. Let's place now our two extrema, which is 1, 1. Here it is. This is the minimum. And negative 1, negative 3. Here it is. And now it's very easy to plot because I have the asymptote, both on the left and the right of each branch, which is going to be something like this. We go to the maximum, and then from there asymptotically to negative infinity. And for the other branch, we come asymptotically from positive infinity to the minimum. And then we continue asymptotically to the lateral, like so. And now let's go ahead and produce the Desmos graph so that we can check the validity of our procedure. So now we can clearly see the graph that is true the way that we have constructed it. Here is the oblique asymptote, the vertical asymptote, which is the y-axis, and here are the extreme points as we have calculated earlier. Now, the last application of derivatives that we are going to see is optimization problems. So they are problems that effectively ask us to maximize or minimize a particular quantity. For example, profits, velocities, quantities, and so on. So we can have an optimized situation and effectively solve the problem. Let's start with an example, an algebraic example. The sum of two non-negative numbers is 20. Find them so their sum of squares is minimum. As with all problems, the difficult part is translating the linguistic description to a mathematical description. So in this case, we want two numbers. We are going to call them x, y, and they are non-negative. It means they can be greater or equal to 0. So this is a restriction, and at the same time the definition of the two numbers. So let's translate these sentences right here. So the sum of the two numbers is 20. So equation 1 is x plus y equals 20. And then we want to find these x and y so that the sum of squares is minimum. So we have 2s equals the sum of squares. So x squared plus y squared. So this is the second equation. And effectively, this is not an equation. This is the function that we want to minimize. The problem is that this function has two independent variables, not one. We haven't done multivariable calculus in this course, nor we will do. So we will have to use this constraint and substitute it into equation 2 so that we can make the sum function to be a function of a single variable, not two variables. So we can take equation 1 and solve it for one of the unknowns, it doesn't matter who. Y equals 20 minus x. So we substitute 1 into 2, and so we get that s of x now equals x squared plus 20 minus x quantity squared. Let's go ahead and expand. We have x squared plus 400 minus 40 times x plus x squared. And let's simplify. So we will get s of x is 2x squared minus 40x plus 400. And this is now a function of a single variable that we need to minimize. So whenever we hear the word minimize or maximize, it means that we need to take ds over dx and make it equal to 0. So this is the condition for either minimization or maximization. So ds over dx equals 4x minus 40 equals 0, and so x will be 40 divided by 4, and so x is equal to 10. So this is a single root of the derivative of the sum. So all we have to do now is verify that for this value s is minimum by constructing the sign table. So we construct the sign table. Notice that the domain of x is from 0 to infinity and not from negative infinity to positive infinity, because x and y as well are positive or 0 numbers. So we place number 10 in the middle, which is a single root, and from the final form of the derivative we can see that the highest order term is positive. So positive, negative, and so we have decreasing and then increasing. So x equals 10 is an extreme point and it is definitely a minimum, and so we have verified that for x equals 10, s of x is minimum. So all we have to do now is find y, and the problem is done. So we are going to use the substitution. Y equals 20 minus x, so y equals 20 minus 10 equals 10. So the two numbers is x equals 10 and y equals 10. And we have finished and solved the problem. So here we have a very simple business problem, that the daily cost of producing x tons of cement in Great Britain's pounds is C of x, 50 plus 70x plus 1/20th x squared, and the daily production of x tons is sold for S of x, 270 minus 3x over 20 per ton. So the problem asks first to find the daily profit function P of x, and B, find the daily production that the factory needs to sell for having maximum profit. So obviously we need to find the quantity x for which the profit becomes maximum, and so the production will be calibrated towards that particular quantity and not more tons, because we will have diminishing returns. So let's start the solution with part A. So we know from basic economics that the profit function is the simple equation of sales minus the costs. So we already have this function for x tons, but the sales function is not the same as the one which is given. The reason is that sales of x tons is going to be the sales of 1 ton times x, so times the quantity that we are going to sell. So in this case, capital S of x will be x times 270 minus 3x over 20 that we are going to expand equals 270x minus 3x squared over 20. And now we can find P of x, which is going to be the sales, 270x minus 3x squared over 20 minus the costs in brackets, 50 plus 70x plus x squared over 20. We can get rid of the brackets by changing all the signs inside, equals 270x minus 3x squared over 20 minus 50 minus 70x minus x squared over 20. So let's collect the like terms. So we will have P of x equals, we have minus 50, then plus 200x, and minus 4x squared over 20, that we can simplify. This one and that one, 1 over 5. So let's tidy this up a bit. P of x is going to be minus 50 plus 200x minus x squared over 5. And this is going to be the daily profit from selling X tons of cement. So we want this function now to maximize it, because this is a quadratic. We can understand from our school years that since a is negative, this function will have a maximum. But let's go ahead and prove it. So for maximizing the profit, we need dp over dx, which is very easily calculated, equals 200 minus 2x over 5 equals 0. So we have 2x over 5 equals 200. And now we can cross multiply the 2/5 on the other side. So we will have x equals 200 by 5 over 2. 200 by 2 is 100 over 1. And then 5 times 100, we will have that x will be 500 tons. And once again, we construct the sign table. Once again, it is illogical to have a negative quantity of cement being produced. So we start x from 0 all the way to infinity. We have p prime and p, and let's place our x, which is 500, again a single root. And now from the final form, we have a negative on the highest order term. So we place minus and then plus on the other side. So we will have increasing, then decreasing. So this is what we said earlier, that beyond the production of 500 tons per day, any additional production of cement will have diminishing returns. So we will produce, but the profits will decrease instead of increasing. So this is indeed a maximum. And so we are going to answer now the problem. The daily amount of cement the factory needs to produce for maximum profit is 500 tons. So you have to be careful about what the problem actually asks. In this case, it asked to find the amount of tons for maximum profit. It didn't ask to find the actual maximum daily profit from the production of the 500 tons. So depending on the questions of the problem, you need to answer those and nothing more, nothing less. So leaving differentiation behind us, we are going to continue with antiderivatives and indefinite integrals. Let's start with a sample. F of x is 3x squared plus 4x plus 5. where each derivative is f prime of x. Let's do it step by step because this is important. Equals. We have 3 times 2x to the 2 minus 1 plus 4 times the derivative of x is 1 plus 0, and so f prime of x is 6x plus 4. Integration is the inverse operation of differentiation. So if we are given the derivative of a function, we can go back to the original function. So let's do the opposite steps that we have done for differentiating f of x. So that to retrieve f of x, we are going to have the derivative, 6x. We are going to increase its exponent by 1. So we have 1 plus 1. And then we are going to divide with the new exponent. So the inverse that we have done here. Divided by 2. And then plus 4 times the derivative of 1 is x. So we are going to replace 1 by x. And so we have that f of x is 3x squared plus 4x. Yes, but we notice that this original function and the actual original function are not exactly the same. So this is not the original function, at least completely. So in order to make the integration consistent, each time that we integrate, we must add an arbitrary constant c to account for anything that is removed during differentiation. So for this result to be consistent with the original function, we need to write it like so, that f of x is equal to the integral of f prime of x dx equals the integral of 6x plus 4 dx, which is going to be 3x squared plus 4x plus c. And so this is much more consistent with the actual function that we differentiated earlier. And so we have that this is a family of functions that one of them is the original. So you might ask how we are going to determine that constant c. So effectively, c is an additional parameter that we don't know just by integrating. So the problem needs to provide additional information. This additional information that we are going to be given in order to find the original actual function, we call them boundary conditions if we are speaking about spatial dimensions, so for example x, y, z and so on, or initial conditions if the function is a time function. So directly let's see an example on how to use the initial or boundary conditions. So in this case we need the original function with a time derivative f prime of t, 5t plus 2, so you can consider this to be the velocity of an object, and the initial condition f of 0, so at t equals 0 at the beginning of the experiment, the initial value of the function, so the position in this case, was 40 meters from the origin. So this is an initial condition because t is equal to 0. So let's go ahead and integrate. F of t will be equal to the integral f prime of t dt, because the integration variable is time in this case and not x, equals to the integral of 5t plus 2 dt equals. So once again we have t to the first, so we increase its exponent by 1 and divide with the new exponent, and this plus 2 times 1 will be multiplied by t. So we have 5t squared over 2 plus 2t plus c, And this is exactly what we call the indefinite integral of f prime of t. Now all we have to do is substitute the initial condition and equate it with 40, and we solve for c. Now very easily this will become f of 0 equals 5 times 0 squared over 2 plus 2 times 0 plus c. This will be equal to 40. This is 0, this is 0, and all it's left is that c is equal to 40. And so the actual function f of t is 5t squared over 2 plus 2t plus 40, and this is it for t greater or equal to 0. So this is the condition. Anyway, we cannot have negative time instances, so we apply this to be effectively the domain of this function. And this is exactly the original function that the problem asks for. So now we can continue with some integration rules. Just like with the differentiation rules, we have the relevant integration rules for integrals as well. So let's start with the power rule. Integral of x to the nth dx equals x to the n plus 1. So we increase the exponent by 1 and then divide with the new exponent plus c, where n is a real number, not necessarily an integer, except negative 1. So what happens when we do have n equals negative 1? Integral of x to the negative 1 dx equals integral of 1 over x dx, and this is ln absolute x plus c. C, the integral of e to the x dx equals e to the x plus c. D, integral of sine x dx equals negative cosine x plus c. E, integral of cosine x dx equals sine x plus c. And then we have the composite functions. F, the integral of f to the n of x times f prime of x dx equals f to the n plus 1 of x over n plus 1 plus c. Once again, n is a real number except negative 1. So let's give an example. The integral of 2x times x squared plus 5 to the 5th power dx. We can clearly see that this is f to the 5th of x, and this is the derivative of the bracket. So we can directly solve this. Equals x squared plus 5 raised to the 6th divided by 6 plus c. G, if we have integral f prime of x over f of x dx, this will give us ln absolute f of x plus c. Let's see another example. The integral of 1 over x plus 5 dx. We can see that this is an f of x, and at the top we have f prime of x. So we can treat it as a logarithmic integral. Equals ln absolute x plus 5 plus c. It is that easy. Then we also have two rules, which basically we already know them from the limits and the derivatives. H, the integral of any constant multiplied by a function dx. The constant can come out of the integral. So this is equal a times integral f of x dx. And lastly, I, if we have the integral of a sum or difference of functions, f of x plus or minus g of x dx, this is going to be equal to the integral f of x dx plus or minus the integral g of x dx. However, keep this in mind that this only works for addition or subtraction, not for multiplication or division. So let's go ahead and see one example. As we can see, we have a large polynomial inside the integral with additions and subtractions. I'm going to execute this step by step using all the rules, and after this point we can execute the integration directly without the intermediate steps. So I is equal, since we have a sum or a difference, we can break them apart. Integral of 3x cubed dx minus integral 4x to the 5th dx plus the integral of 2x squared dx plus the integral of 5x dx minus the integral of 2 dx. We can see now that we have functions multiplied by constants, and the last one is the integral of a constant. So we can take them outside. Equals 3 times the integral of x cubed dx minus 4 integral x to the 5th dx plus 2 integral x squared dx plus 5 integral x dx minus 2 integral dx. So now all we have to do is execute the power rule. The only difference is that this last one is integral of dx, so this will give us x equals 3 times x to the 4th over 4 minus 4 times x to the 6th over 6 plus 2 times x cubed over 3 plus 5x squared over 2 minus 2x plus c. And let's check if we have any simplifications. We do 4 over 6 is 2 over 3 and nothing else. And so we have I equals 3x to the 4th over 4 minus 2x to the 6th over 3 plus 2x cubed over 3 plus 5x squared over 2 minus 2x plus c, and this is the final result. Let's see now another example. I equals the integral of e to the x over 5 plus 2 cosine x minus 1 dx. So now we can see that we have once again a sum of terms, that some of them are multiplied by a constant. So we can just copy and paste them, and then we multiply those with the respective integral of these terms. So we can write directly I is equal to e to the x over 5 plus 2 sine x minus x plus c. And this is the result. Let's see another example. I is equal to the integral of x squared plus 5x plus 3 all divided by x dx. But we haven't learned a rule that has a quotient. So the only thing that we can do is effectively break the fraction apart and see if we have any simplifications. We are lucky because the denominator is a single term. So we can say equals the integral of x squared over x plus 5x over x plus 3 over x times dx. We can simplify the square with x and x with x, 1 over 1, and let's break them apart. I is equal to the integral of x dx plus 5 times the integral of dx plus 3 times the integral of dx over x. So now we can solve this very easily. I is equal to x squared over 2 plus 5x plus 3 ln absolute x plus c. Let's see another one. I is equal to the integral of x times x minus 2 dx. Once again, we haven't seen a rule with multiplication, and x is not the derivative of the interior of the brackets, so all we have to do is expand, which is also very easy. So we have I is equal to x squared minus 2x dx, and now we can integrate term by term. I is equal to x cubed over 3 minus 2x squared over 2 plus c, which we can simplify. And so I is equal to x cubed over 3 minus x squared plus c. And this is the result. So what happens if we have this? I is equal integral root x minus 1 over root x dx. We haven't learned a rule about roots. However, we know that each of these roots can be translated as a power of x. Let us remind ourselves that the square root has a index of 2 that is implied, and so the index of the root is the denominator of the exponent. So this can be written very easily. I is equal to the integral of x to the 1/2 minus 1 over x to the 1/2 dx, but also this 1 over x to the 1/2 can be also being brought to the numerator just by changing the sign of the exponent. I is equal integral of x to the 1/2 minus x to the negative 1/2 dx. And now once again it's the power rule. It doesn't matter if it's a fraction, we increase it by 1 and then we divide with the new exponent. Equals x to the 1/2 plus 1 divided by 1/2 plus 1 minus x to the negative 1/2 plus 1 divided by negative 1/2 plus 1 plus c. And let's do the operations now. Equals x to the 3/2 divided by 3/2 minus x to the 1/2 divided by 1/2 plus c. And now we can simplify these composite fractions. Equals 2/3 x to the 3/2 minus 2x to the 1/2 plus c. And we can leave it in this form. If we want to be tedious, we can turn these back into roots and say this is equal to 2/3 of square root of x cubed minus 2 square root of x plus c. Lastly, let's see another one. I is equal to the integral of cosine cubed x dx. We can clearly see that this is an integral of f to the nth of x dx, not the integral of f to the n dx times f prime of x dx. So these two are not the same. We are not multiplied with the derivative of cosine, so we cannot use the power rule. Instead, we are going to exploit the trigonometric identities and make a small transformation to this one to make it more manageable. So I is equal to the integral of cosine x times cosine square x dx, and we know that cosine square x is translated to 1 minus sine square x equals the integral of cosine x times brackets 1 minus sine square x dx. And now we can expand like so, equals the integral of cosine x dx minus the integral of cosine x times sine square x dx. Now this is easily solvable because it's one of the basics, and here we have f to the nth, f squared, times the internal derivative. So this integral, this second integral, follows this rule, so we can definitely use it. And this is going to be I is equal to sine of x minus sine cubed of x over 3 plus c. And this is going to be the result. Let us continue now with integration by substitution. Let's start with an example. I is equal to the integral of 2x cosine of x squared plus 1 dx. Okay, so we can recognize this, if we have keen eyes, that this is the integral of cosine f of x times f prime of x dx. And this will give us the sine of f of x plus c. So this is an easy case, so we can write directly that this is I, the sine of x squared plus 1 plus c. And let's take it as a given for checking our technique. Now, if we don't have keen eyes or we are relatively inexperienced, we couldn't have seen that this is the internal derivative of the function inside the cosine. So we can take this function that is the problematic one and substitute it with another variable, an intermediate variable, and hopefully we can make this easier to solve. So we can do by substitution, or this is also called u sub, and the reason being we are going to be substituting the problem part with the variable u. So let's call this u equals x squared plus 1, but in order to make a substitution inside an integral, we need to substitute everything that has to do with x, including the differential. So we know that du over dx is going to be 2x, but if we want to turn this into a differential, we simply cross multiply by saying du equals du over dx times dx, and so this is going to be equal to du equals 2x dx of u of x. So using this, we can see that I is equal to the integral of cosine x squared plus 1, but let's bring the 2x on the other side of the cosine function, times 2x dx, and we can clearly see that if this is u inside the cosine, this is du. So let's do the substitution. Equals the integral of cosine u times du, and this is now a basic integral that turns into a sine. So this is equal sine of u plus c, but the final result must not have the intermediate variable, so we are going to substitute back the expression that we have substituted with u, and so I is equal to sine of x squared plus 1 plus c, and this would be our result, which is exactly the same result that we found in the beginning of the exercise. Continuing on, we have I equals the integral of square root x plus 1 dx. So we can substitute either the entire root or the quantity inside the root. So let's do the latter. U equals x plus 1, x equals u minus 1. So this is going to be helpful for finding the differential of x. So dx is going to be d of u minus 1. So effectively we differentiate and we multiply it with the differential. That's it. So dx is du, and we need that as well. So I is equal to the integral of the square root of u times du, and this is once again an easy integral because the square root can be converted into an exponent. This is equal to integral of u raised to 1/2 du, which is 2 over 3 times u 3/2 plus c. And now we can reintroduce what we have substituted as u, which is x plus 1. And so the final integral, I is equal to 2 over 3 times x plus 1 to the 3/2 plus c, or we can turn it into a root once again, equals 2 over 3 the square root of x plus 1 quantity cubed plus c. This is also solved if we have keen eyes. I is equal to the integral of the square root of x plus 1 dx. We can see that this is f of x, and it is multiplied by 1, which effectively is f prime of x dx. So without thinking about it, this will become 2/3 the square root of x plus 1 quantity cubed plus c, directly without thinking about it. Another example, I is equal to the integral of x times the square root of x plus 1 dx, where in this case we have the square root of f of x, but this is another function which doesn't have anything to do with the derivative of the f of x. So without thinking about it, we are going to substitute. For this example, let's use the entire square root as the substitution. So u is going to be the square root of x plus 1, and we need to solve for x. So first of all, we need to square both sides. U squared equals x plus 1. X is equal to u squared minus 1. So we are going to use this to substitute that plain x over there. And also it will help us to calculate the differential dx. So dx is going to be the derivative of u squared minus 1. So it's going to be 2u, and then we multiply by the differential du. So we want this one, and that one. I is equal to integral x is u squared minus 1 brackets times the substitution, which is u, times 2u du. So we have substituted everything. Let's tidy this up a bit. This is equal to integral of u squared minus 1 times 2u squared du. And also, because we have, once again, multiplication that we know no rules about, we can simply expand the brackets, like so, equals the integral of 2u to the 4th minus 2u squared all du. And this is once again a basic integral. We have made this complicated one into this simple one. And now we are ready to integrate. Equals 2/5 u to the 5th minus 2/3 u to the third plus c. And now let's bring once again the square root back into the solution, which is going to be I 2/5 the square root of x plus 1 quantity to the fifth minus 2/3 the square root of x plus 1 quantity cubed plus c. And this is going to be our result. Now let's see another example. I is equal to the integral of x squared divided by the square root of 1 minus x squared quantity cubed dx. In this case, we are given the substitution directly. X equals sine theta, where theta is between 0 and pi over 2. Once again, this is a given substitution because this is probably quite difficult to think of what substitution to use. Indeed, let's try to substitute the function underneath the square root. So let us try. U equals 1 over x squared. So x squared is 1 minus u. And so 2x dx equals minus du. So let's go ahead and substitute on the integral. I is equal to the integral. We have already an x squared, which is 1 minus u divided by the square root of u cubed times what? Because dx is multiplied by 2x. It means that we also have an x to take care, but we cannot solve for x because we would have a square root. So this will become very difficult, and so the regular substitution is not working. So instead, since we are given the substitution directly, we can find dx without any problems. So dx is going to be cosine of theta times d theta. And let's go ahead and substitute on our integral. I is equal to the integral of x squared over the square root of 1 minus x squared quantity cubed dx equals the integral of sine squared theta divided by the square root of 1 minus sine squared theta quantity cubed times cosine theta d theta. Because this is dx, we are going to substitute everything. Also, we can see that inside this bracket we can construct a cosine squared, because if we remember, sine squared theta plus cosine squared theta equals 1. This is the Pythagorean and most basic trigonometric identity. If we bring the sine square on the other side, we are left with cosine squared equals 1 minus the sine square. So this becomes very easy. Equals the integral of sine squared theta times cosine theta divided by the square root of cosine squared theta quantity cubed d theta. We can take that exponent outside the square root, and now we can see that we have a square root of a square. So let's remind ourselves that the square root of x squared is not equal to x, but absolute x. Keep this in mind because this is very important. So let's do this first. Equals to the integral of sine squared theta times cosine theta divided by the absolute value of cosine theta quantity cubed d theta. The thing is that we cannot do any operations while we have the absolute value, so we have to find the sine of cosine in those limits that were given in the beginning. So by constructing the trigonometric circle, and also we have 0 less than theta less than pi over 2, it means that we are on the first quadrant. And so the cosine theta is positive, and so the absolute value of cosine theta will be simply equal to cosine theta. We just remove the absolute values. And so I is equal to the integral of sine squared theta times cosine theta divided by cosine cubed theta d theta. We can see that we have a simplification of cosine with the cube, which makes it a square, and now we can write it equals the integral of sine squared theta divided by cosine squared theta d theta. We cannot integrate this function directly because the sine squared is not the derivative of cosine squared. So we can use the trigonometric identities once again, equals the integral of tan squared theta d theta, but the integral of tangent square is not a basic integral, so we have to use yet another identity, which is 1 plus tan squared theta equals secant squared theta, which we know secant squared theta is the derivative of tangent theta. So we are going to exploit this and make it equal to the integral of secant squared theta minus 1 d theta, and this is a simple integral to integrate term by term, so this will become tan theta minus theta plus c, but now we need to find a way to get rid of theta. So let's remember that x is sine of theta, so we don't have tangent of theta directly, and we also don't have a relationship about theta. Yes, but we can solve the substitution for theta by taking the inverse sine function and saying that theta is arc sine of x, or we can say sine to the negative 1 of x, which means the inverse sine, not 1 over sine. And also we need a right triangle to help us understand how to find the tangent of theta. There is the expression of tangent of theta based on x. So this is our right triangle. If we consider this to be theta, which is an acute angle, we can clearly see that the sine of theta, which is the opposite over the hypotenuse, this is equal to x over 1, let's not forget. So the ratio of the opposite, which is going to be x divided by the hypotenuse, which is 1. And now, using the Pythagorean theorem, we can say that the other side, 1 squared equals x squared plus b squared. Let's call it b. So b squared is 1 minus x squared, and so b is going to be the positive root 1 minus x squared. We don't need the negative because this is a length. So we replace 1 minus x squared, and now the tangent is the opposite over the adjacent. So tan theta is x over the square root 1 minus x squared, and now we simply throw it onto the result of the integral and we are finished. So I is equal to x over the square root of 1 minus x squared minus the arc sine of x plus c, and this is the result. Continuing on, we have integration by parts. So in many cases we have integrals that are products of functions that are not of the type function internal derivative, like so integral f of x times f prime of x, nor they are of the same type. What we mean by type, it means that in the product of the functions, both of them are trigonometric, they are algebraic, or so on. They are not of the same type, so we are going to use this technique, integration by parts. So the technique is like so. The integral of u times dv over dx dx is equal u times v minus the integral of v times du over dx dx, where u equals u of x and v is equal v of x. So both of these u and v are functions of x. As mentioned, these u and v are not of the same type, and also they don't have any relationship between them, so we are going to use this technique, and also this technique is the last resort whenever we want to solve an integral of a product of two functions. So from the definition of the technique, you can see that the u function is a function that is going to be differentiated, where v is going to be integrated. So u is something to be easily differentiable, where dv over dx dx is something to be easily integratable. So effectively we have a priority on which function of the two in the product to take as u. So this priority starts with first logarithmic, then 2 inverse trigonometric, third algebraic. So effectively they are polynomial, rational, radical, and so on. 4 trigonometric, and lastly number 5 exponential. So the priority of this, as you can see, we opt to take as u of x the inverse functions, the ones that we learn later in our school career, and we leave the trigonometric and the exponential functions as the last priority because they can be integrated and differentiated easily. So the priority starts from the top and goes to the bottom like so, and we are going to use this guide in the following examples. So we have I is equal integral x times e to the x dx. So first of all we can see that we have a polynomial function, x is algebraic, and e to the x is exponential. So this is going to be u, and this will be dv. So we are going to use this guide, u equals x, which is going to be differentiated. So du equals dx, where we have dv to be equal e to the x dx, that we integrate left and right, and so we are left with v equals e to the x. So we have I equals v times u, so x times e to the x minus the integral of v times du. So we have e to the x dx, but now this is a basic integral and we don't need to repeat the procedure. So we simply write equals x e to the x minus e to the x plus c, and if we wanted we can factor out 1 e to the x and write I equals e to the x times x minus 1 plus c, and this is the result. Let's see another example. I equals the integral of x squared minus 1 times sine of x dx, where we can see we have an algebraic once again and a trigonometric this time. So as u, we will take the x squared minus 1. Let's find its differential. Du equals the derivative of x squared minus 1, which is 2x, times dx, and dv is sine of x dx, which will integrate left and right. And we have that this is going to be negative cosine x. So I is equal u times v, which is minus brackets x squared minus 1 cosine x minus the integral of v times du, which is 2x times minus cosine x dx. Once again, we have another algebraic and a trigonometric. Maybe we can tidy this up a bit. Equals minus x squared minus 1 cosine x. Then minus times minus is positive. And also that times 2 we can take it outside. So 2 times the integral x cosine x dx. So let's repeat the process. We still have a product of an algebraic and a trigonometric. Let's use a different color set. U is x, du equals dx, and dv is cosine x dx, which we integrate, and v equals sine x. So this is going to be equal minus x squared minus 1 cosine x plus twice, and then we open brackets because this integral will become a sum. So u times v, which is x sine x minus the integral of v times the u, which is sine x dx. And once again, we have a simple and basic integral that we can solve directly. So equals minus x squared minus 1 cosine x plus 2 times x sine x minus the minus cosine x plus c. And now we can tidy this up. We can also expand if we like to reach the result. I is equal minus the x squared minus 1 times cosine x plus 2x sine x plus 2 cosine x plus c, and this is the final result. So what happens if we have this integral? I is equal the integral of ln of x dx. So effectively we don't have a product, but we have the integral of ln of x. This is the inverse exponential function, the logarithmic function, that we must be able to integrate. The trick is here that ln of x is also multiplied by 1. So obviously, clearly, ln of x will be the u function and dx will be dv. So u is ln of x, du is 1 over x dx, then dv is dx, then we integrate and we have v equals x, and let's go ahead and use them. I is equal u times v, which is x ln of x minus the integral of v times the u, which is x times 1 over x dx. Here we have a very pretty simplification, 1 over 1, which is left equals x ln of x minus the integral of dx. And this is the simplest integral that we can have, which is going to give us a simple x. And so I is equal x ln of x minus x plus c. And we have managed to solve this difficult, inconceivable integral just by using integration by parts. And effectively, once again, it's the last resort. We don't have any other ways of manipulating this function, so we must use the integration by parts. Let's see another example. I is equal to integral e to the x cosine x dx. Here we have a product of an exponential and a trigonometric function. So obviously the trigonometric has a higher priority for u, cosine x, du equals minus sine of x dx, and dv is e to the x dx, integral, and v is e to the x. So I is equal u times v, so e to the x cosine x, minus the integral of v times du, which is e to the x times minus sine x dx. We can take this negative sign on the outside, equals e to the x cosine x plus the integral of e to the x sine x dx. And once again we have a trigonometric and an exponential. So we use the technique once again. U is equal sine of x and du equals cosine of x dx, and dv is e to the x dx, integral, and v is e to the x once again. So this is going to be equal, copy and paste the first term, e to the x cosine x, then plus u times v, which is e to the x sine x, minus the integral of v times du, which is e to the x cosine x dx. But you will notice that we have reached once again the same position as the one that we have started, plus a couple of more terms. Yes, but we can recognize that this is the original integral. So we can call this I. So I is equal to these two terms minus itself. So we can bring this on the other side and have 2i's equals e to the x cosine x plus e to the x sine x, which we can factor out that e to the x equals e to the x times cosine x plus sine x. And so the I integral is this guy divided by 2. So e to the x over 2 times cosine x plus sine x and plus c at the end. And this is the result. So this is the reason why I tend to use this variable I, basically to assign the value of the integral to that variable. And also, it's very helpful when we have these kind of situations, so that we can recognize that this is I, we substitute the variable I, and then we overcome this difficulty that we have in these problems. So finally, let's see some examples on how to integrate composite trigonometric functions, starting with I is equal to the integral of cosine square x dx, where once again we don't have f squared times f prime of x. This is simply f squared. Because this is not multiplied with its internal derivative, it means we cannot use that rule, the power rule. But remember that we have trigonometric identities that we can reduce the order of the cosine and make it cosine to the first, something that we can integrate very easily. Let us remind ourselves that cosine square x is 1 plus cosine of 2x divided by 2. Let's substitute it on our integral. I is equal the integral of 1/2 times 1 plus cosine of 2x dx. We can take that 1/2 outside. 1/2 the integral of 1 plus cosine 2x dx. So let's go ahead and solve this. Equals 1/2 brackets x plus the integral of cosine 2x dx. But for this to be solved, it was supposed to be multiplied by times 2. We can do that by multiplying the times 2 that we need, but at the same time, we need to multiply outside the integral with its reciprocal, 1/2, so that that times 1 that was originally there is maintained. Now we are ready. This is a constant. This is the function times its internal derivative. So nothing stops us now to solve this. Equals 1/2 times x plus 1/2 the sine of 2x plus c. And so if we expand, we can have I is equal x over 2 plus sine of 2x over 4 plus c. And this is the integral of the composite cosine squared. Let's continue with the final example. I is equal to the integral of cosine cubed x divided by 1 minus sine x dx, where x is in the first quadrant, so from 0 to pi over 2, not included. So obviously we don't have an identity for cosine cubed, but we have for cosine squared. So let's rewrite this. I equals the integral of cosine x times cosine squared x over 1 minus sine x dx, that we can now translate into integral the cosine x times 1 minus sine square x divided by 1 minus the sine x dx. Now we can clearly see the relationship between the denominator and this bracket on the top. Not only this is a trigonometric identity, but it also doesn't stop of being a difference of squares. So we can factorize this and have a simplification with the denominator. So this is equal to integral cosine x times 1 minus sine x times 1 plus sine of x divided by 1 minus sine x, that we can simplify now, 1 over 1, and also times dx. And let's see what we are left with, equals the integral of cosine x times 1 plus sine x dx, that we can expand, and we are going to have equals the integral of cosine x plus sine x cosine x dx, that we can easily solve because this is a basic integral, and also this guy is a function times its internal derivative. So we can say equals sine x plus sine square x over 2 plus c. So someone might have an objection. Why use the sine as f of x and cosine as the derivative and not the other way around? Of course, we can use that logic and have this result instead, equals the sine of x plus the negative cosine squared x over 2 plus c, which is going to be sine x minus cosine square x over 2 plus c. They are both valid. Also, a third person may have an objection by treating this as 1/2 of sine of 2x. Let's remember that sine of 2x is 2 times sine x cosine x. So you might say that we can turn this into an even easier function to integrate, which is going to be equals the integral of cosine x plus 1/2 sine of 2x dx, which is going to be the sine x plus 1/2 times cosine of 2x over 2 plus c, which is also sine x plus cosine of 2x divided by 4 plus c. And obviously these three versions are equally valid, and the reason is because we have that plus c at the end. Obviously in every case we will have a different value for this constant, but because we have that arbitrary integration constant given by the integration process, we can have different versions of the original function, and the only thing that is going to be different in those versions is the value of that constant c. So thank you for your attention, and I will see you all next week.